KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we start with the 9th exercise problem. See here. So first we will go through the problem, then we will come to the solution or answer. Okay, right. See here. A 12.75 electron volt electron beam is used. So this is what energy, 12.75 electron volt electron beam is used to bombard gaseous hydrogen at room temperature. To bombard gaseous hydrogen at room temperature. Full stop. What series of wavelengths will be emitted? What series of wavelengths will be emitted? Okay. So what I am saying is, observe carefully. It is what a 12.75, a 12.75 electron volt electron beam is used to bombard. So like collision, right? So to bombard gaseous hydrogen at room temperature. Gaseous hydrogen at room temperature. He is asking what series of wavelengths? What series of wavelengths will be emitted? Okay, right. Listen carefully, because here problem is simple, but we need to calculate multiple wavelengths. Okay, many more number, right? See here. First, given value, that is what delta E is equal to 12.75 electron volt, right? This formula, that is what yesterday also, in our previous problems also we discussed that. That is what energy of an electron in nth orbit of hydrogen atom is. Energy of an electron. Energy of an electron in nth orbit. Energy of an electron in nth orbit of hydrogen atom is En is equal to minus 13.6 divided by n square electron volt is a formula. It is a formula, I will repeat once again. Is an important formula. I already told you, right? Is a formula important for NEET and mains also. Energy of an electron in nth orbit of hydrogen atom is En is equal to minus 13.6 divided by n square electron volt. Okay, right. In ground state, so when n is equal to 1, E1 is equal to minus 13.6 1 square. N square is there, no? So here 1 square is equal to minus 13.6 electron volt. This is what energy of an electron in ground state. That is what minus 13.6 electron volt. Okay, right. Next, see here. Energy of an electron in the excited state after absorbing a photon of 12.75 electron volt energy, right? Energy of an electron in the excited state. Energy of an electron in the excited state after absorbing a photon. After absorbing a photon of 12.75 electron volt energy becomes, right? So what is the energy of an electron in the excited state after absorbing this much amount of energy in the form of photon? That is what 12.75 electron volt will be like this. See this, En is equal to minus 13.6 plus 12.75. So what is the balance? Minus 0.85 electron volt. Minus 0.85 electron volt is that is what remaining, the balance energy, right? So the energy which is balanced, right? See here, which is balanced means what? Remaining amount of energy. Remaining amount of energy will be, that is what? 0.85 electron volt, right? So which is 0.85 electron volt means you can find out the level, you can find out the excited state. You can find out the excited state by using the same formula, that is En is equal to minus 13.6 by n square. Okay, that is what from this formula you can write n square as a subject. N square is equal to minus 13.6 by En. That only he is writing here. Minus 13.6 divided by minus 0.85. Okay, so it will give us 16. When n square is equal to 16, n is equal to 4, right? So thus the electron gets excited to n is equal to fourth state. Thus the electron gets excited to n is equal to fourth state. Okay, right. Next, see here, total number of wavelengths in emission spectrum. Total number of wavelengths in emission spectrum, right? You can see this picture also, that is what right, you can observe, and before that you see this, that is what the formula to calculate total number of wavelengths in emission spectrum based on the n value, that is n into n minus 1 by 2, that is equal to 4 into 4 minus 1 by 2. 4 minus 1 means 3, so here you will get it as 6. So 6 number of wavelengths we will get it. Okay, right. Finally, emitted wavelengths, emitted wavelength lambda IF, lambda I means initial, F means final. So lambda IF is equal to general formula HC by EI minus EF, EI minus EF, that is 6.6 into 10 to the power of minus 34 into 3 into 10 to the power of 8 divided by EI minus EF, EI minus EF, that is equal to here 19.8 into 10 to the power of minus 26 by EI minus EF meters, right? So it is like a formula. He won't talk about the wavelengths what we need to find according to the problem, right? Just it is a formula. It is a formula, and these two are the constant values, no. But these two will vary based on the situation. So from where to where the electron is going, right? So it depends upon that. That's why these two varies, but these two are constants anywhere, no. Planck's constant and speed of light. Okay, that's why he used to do this mathematical process, and he is giving this value, right? So now in this problem, to calculate a series of wavelengths, you can use this formula, that is what? 19.8 into 10 to the power of minus 26 by EI minus EF, EI minus EF meters. Okay, right. Okay, now we are going to calculate series of wavelengths, right? You see this, that is what here emission lines, right? The possible emission lines according to this question. Okay, right, there are 4, that is what ground state, that is like n is equal to 1, and n is equal to 2, n is equal to 3, n is equal to 4, right? There are 6, 1, 2, 3, 4, 5, 6. Okay, so I will repeat once again, 1, 2, 3, 4, 5, 6, right? So 6 different wavelengths we have to find. We can calculate. Okay, right. See, one by one I will tell you. Here lambda 4, 3. So it is 4, it is 3. See here, same formula, 19.8 into 10 to the power of minus 26 divided by EI minus EF. See here, it is what? So it is 4, it is 3. It is minus, it is what? 0.85, and it is what? 1.51, and minus of minus means here plus will come. So minus 0.85 plus 1.51 into 1.6 into 10 to the power of minus 19. So that you will get it as 9.8 into 10 to the power of, and I mean it's a mathematical process, right? So from here to here nothing is there, right? So you just do the mathematical process. you will get the answer, right? I need not to say what will happen here, because it is just multiplication, and here also multiplication, finally here division. You will get the answer like this, right? And then finally if you convert into angstrom unit, right? So by knowing, as a student, by knowing what is the relation between angstrom unit and meter, it is very simple thing, right? So that's why up to here only we this is that like physics part, right? So from here to here it is a mathematical part, and you have to know the relation between angstrom and meter, okay, right? So here it is, you will get it as 28,409 angstrom unit. That is what first wavelength, I mean here lambda 43, right? So regarding these two, this is the wavelength emitted. Next lambda 42, so these two 4 and then 2, okay, right? See here, same formula, that is what 9.8 into 10 to the power of minus 26 by EI minus EF, right? So 4 2, it is like minus 0.85 minus of minus 3.4, see here, into 1.6 into 10 to the power of minus 19. Here we are getting, do the same process. How we are doing like this? Similarly you do that. Finally you will get it as 4,852.9 4,852.9 angstrom units, okay, right? Next see here 4.1, same process, 19.8 into 10 to the power of minus 26 minus 0.85 into 13, okay, right, minus of minus, anyhow it is plus 13.6 into 1.6 into 10 to the power of minus 19. Finally 970.6 angstrom units, okay, that's it. So next lambda 32, so from here to here, same, that is 19.8 into 10 to the power of minus 26 divided by EI minus EF, right? So here it is EI, it is EF, see here, into 1.6 into 10 to the power of minus 19, right? That is equal to, why we are writing 1.6 into 10 to the power of minus 19 means just we are converting into joules, so that you will get the answer in meters, right? After that automatically you can convert from meters into angstrom units, okay, that's it, that is the only thing. Next here we are getting 970.6 angstrom unit, right? And here when you are taking 3 to 2, lambda 3 into 2, that is lambda 3 2, you will get it as 6,547.6 angstrom units, okay, right? Next lambda 3.1, okay, lambda 3.1 is equal to 19.8 into 10 to the power of minus 26 divided by, it is minus 1.51 plus 13.6 into 1.6 into 10 to the power of minus 19 will give us 1023, right? 1023.6 angstrom unit is a wavelength, corresponding wavelength when transition takes place from 3 to 1. Next last wavelength, right? Because here we had only 6 now. Total number of wavelengths in emission spectrum according to this question is 6. So lambda 2.1, so 2 to 1 so 19.8 into 10 to the power of minus 6 divided by minus 3.4 plus 13.6, right, into 1.6 into 10 to the power of minus 19 is equal to 1213.2 angstrom units, okay, right? So this is all about this problem. So in this problem, right, he is asking to find series of wavelengths will be emitted, right, by giving some energy of the photon which is going to bombard with a, right, a gaseous hydrogen, right? So at 12.75 electron volt, electron beam, right, electron beam is used to bombard gaseous hydrogen at room temperature. So these are the series of wavelengths. So what I told you, lambda 43, lambda 42, lambda 41, lambda 32, lambda 31, lambda 21, right? So these are the wavelengths which will be emitted, okay, right? Next question, 10th question, see here. In accordance, right, in accordance with the Bohr's model, in accordance with the Bohr's model, find the quantum number that characterizes the Earth's revolution around the Sun in an orbit of radius 1.5 into 10 to the power of 11 meters, right? 11 meters with orbital speed 3 into 10 to the power of 4 meters per second. 3 into 10 to the power of 4 meters per second. Try to understand the question. In accordance with the Bohr's model, find the quantum number that characterizes the Earth's revolution around the Sun in an orbit of radius 1.5 into 10 to the power of 11 meter with orbital speed 3 into 10 to the power of 4 meters per second. And in this problem, to solve this problem, to find whatever he is asking, that is what quantum number, we need mass of Earth also, that is actually constant value, right? It is 6.0 into 10 to the power of 24. 6.0 into 10 to the power of 24 kg. 6.0 into 10 to the power of 24 kg. Okay, right. And see here, according to Bohr's quantization, condition of angular momentum. According to Bohr's quantization, condition of angular momentum, that is what angular momentum of Earth around the Sun, which is from Bohr's postulate also, that is what mvr is equal to n into h by 2 pi. In this problem, we are comparing the atomic model to the that is what Earth's model, that is which is present in our solar system, right? Here, that is what how electrons are revolving in the nucleus. How electrons are revolving surrounding the nucleus. That is what atomic structure. He is comparing that situation to the situation which is present in solar system, right? So there itself we can talk about the angular momentum of Earth around the Sun, right? So Sun is like the nucleus and Earth is like the electron which is revolving in its own orbit, right? So here mvr is equal to n into h by 2 pi. So n is the quantum number. If you write n as a subject, 2 pi mvr by h. So 2 pi 3.14 into m 6 into 10 to the power of 24 into v 1.5 into 10 to the power of 11 into 3 into 10 to the power of divided by 6.6 into 10 to the power of minus 34 is equal to 2.57 into 10 to the power of 74. The answer will be, the quantum number will be 2.57 into 10 to the power of 24 is a quantum number. Okay, right. Next problem, that is 11th problem here according to our textbook. See here, answer the following questions. Okay, right. So they have given some questions. These questions helps us to understand the difference between Thomson's model and Rutherford's model better, because already the first exercise problem I told you, there also is one question, that is first exercise problem. There also we understood the difference between Thomson model and Rutherford's model. And with this question, again we are going to discuss the difference between Thomson model and Rutherford's model, which will help us to understand somewhat deeper, somewhat better these two models, which are very important models. One is Thomson, another one is Rutherford's. Okay, right. So answer the following questions, right? Okay, ma. So here we have 4 questions. Right? So here we have 4 questions. First I will read you a first question, then I will go for answer. Then I will go for next question B, and then I will go for answer, and then C, answer D, like that. Okay, because I am explaining all the questions, all the answers means you may not catch up, right? So first question is the average angle of deflection of alpha particles by a thin gold foil predicted by Thomson's model much less, about the same, or much greater than that predicted by Rutherford's model. The question is the average angle of deflection? You know that gold foil is there, alpha particles are going to pass through the gold foil, some of the alpha particles will come back to the same path, that is okay, and some of the particles less than 90 degrees scattering, some of the particles greater than 90 degrees scattering, right, some of the particles undeviated, right, you know that situation you have to keep in mind, right. So by keeping that situation in our mind, see this question, that is what is the average angle of deflection of alpha particles by a thin gold foil predicted by Thomson model. Gold foil predicted by Thomson's model much less, about the same or much greater than that predicted by Rutherford's model. So he is asking to compare average angle of deflection of alpha particle, that is what from Thomson model to Rutherford's atomic model. Okay, right. You know, see the answer. That is what about the same. This is because we are considering the average angle of deflection. This is because about the same, right? This is because we are considering average angle of deflection, right? So because of considering average angle of deflection, right? So which is same in both the models, that is what Thomson's model and Rutherford's atomic model, that is average angle of deflection of alpha particles. Next, see next question, that is what B. See here. So in case of B, observe carefully. In case of B, is the probability of backward scattering, So what is meant by backward scattering? You know, what is meant by backward scattering, right? So backward scattering means scattering of alpha particles at angle greater than 90 degrees. Backward scattering means scattering of alpha particles at an angle greater than 90 degrees. Okay, right. Is the probability of backward scattering predicted by Thomson's model much less, about the same, or much greater than that predicted by Rutherford's model? So out of these three, you have to select one. That is what much less, about the same, or much greater. Right. The answer is, much less, because there is no such massive core, in Thomson. Massive core means nucleus, massive core means nucleus, right? Much less, because there is no such massive core in Thomson's model as in Rutherford's model, okay. So first answer and then reason. Okay, right. Next, C. Keeping the factors fixed, it is found experimentally that for a small thickness small t, the number of alpha particles scattered at moderate angles is proportional to small t. So what he is saying, keeping the other factors fixed, it is found that experimentally the number of alpha particles scattered at moderate angles is proportional to the thickness t. Right? Full stop. What clue does this linear dependence on t provide? What clue does this linear dependence on small t provide? Okay, right. So that we have to answer. Right. He is asking the relation. Okay, ma? Right. See this. This suggests that scattering is predominantly due to a single collision. This suggests that scattering is predominantly due to a single collision, because the chance of a single collision increases linearly with the number of target atoms and hence linearly with the thickness of the foil, right. So the relation is linear, but he is telling how it is linear. So this suggests that the scattering is predominantly due to a single collision, because the chance of a single collision increases linearly with the number of target atoms, and hence linearly with the thickness of the foil, that's what he is saying, right. So once again I will repeat, scattering predominantly due to a single collision, because the chance of a single collision increases linearly with the number of targeted atoms and hence linearly with the thickness of the foil, okay, right. Next one, the last one, right. In which model is it completely wrong to ignore multiple scattering for the calculation of average angle of scattering of alpha particles by a thin foil? I will repeat the question once again. In which model is it completely wrong to ignore multiple scattering for the calculation of average angle of scattering of alpha particles by a thin foil? Okay, right. So he is asking about one statement, that is multiple scattering for the calculation of average angle of scattering of alpha particles by a thin foil. Right. See here, in Thomson's model, positive charge is distributed uniformly in the atom. This point we know, right. So here, because of this, single collision causes very little deflection. There is no space, I am saying, you listen, right. In Thomson model, positive charge is distributed uniformly in the atom. So single collision causes very little deflection, right. Okay. See, the observed average scattering angle can be explained only by considering multiple scattering. Hence, it is wrong to ignore multiple scattering in Thomson's model, right. So we cannot ignore. It is wrong to ignore multiple scattering in Thomson's model. Right. So because he is saying that is only in Thomson's model, positive charge is distributed uniformly in the atom. So single collision causes very little deflection. So the observed average scattering angle can be explained only by considering multiple scattering. Hence, it is wrong to ignore. So we can't ignore. The answer is we cannot ignore. See here, we cannot ignore multiple scattering in Thomson's model. He is asking in which model, no? So in Thomson's model, okay, right. So in this class we discussed 3 problems. In first problem, by knowing that is what energy of the photon or energy of the electron beam which is going to use to bombard gaseous hydrogen at room temperature, we calculated series of wavelengths. In second problem we calculated that is what a quantum number, right, quantum number that characterizes the Earth's revolution around the sun by having orbital radius and speed and mass of the Earth. In last problem, and in this class last problem, 11th problem, we discussed some of the questions, right, which helps us to understand Thomson's model over Rutherford's atomic model completely or in deep. Okay, right. Thank you. We will continue in the next class.